Find the minimum value of the function f of x. In this problem, we've been provided a quadratic function f of x and a starting point x0 at 0, 0. We're told to use the conjugate gradient algorithm to find the minimum value of the function, which is represented by the green surface and varies as a function of the variables x1 and x2. We notice we've been provided f of x in the form 1/2 x transpose qx minus x transpose b. Therefore, we'll extract the n by n matrix Q for later use during the algorithm. To find the minimum value of f of x, we want to start at our initial point x0, then move down gradient on the surface f of x to a lower point x1, and then go down gradient again to yet a lower point x2, and continue doing this until the gradient of f of x equals 0, which means we found a local minimizer. To begin, we'll expand our equation for f of x, where our x vector is the generic x1, x2. Next, the gradient of f of x, g of x, equals the partial derivatives of f of x with respect to x1 and x2. Next, we'll evaluate the gradient at our initial point x0, which equals -3, -1. This means to increase the value of f of x, we'd move from x0 in the direction vector where x1 equals -3 and x2 equals -1. However, since we want to minimize the value of f of x, we'll move in the opposite direction vector where x1 equals +3 and x2 equals +1. To find our next position, x1, we'll use the equation xn plus 1 equals xn plus alpha n times dn. At this point, n equals 0, so we can plug in x0 and d0, but we still need to find the value of alpha 0. In this equation, x0 represents the current position vector of our point. d0 represents the direction vector following the steepest descent from our initial point. And variable alpha 0 is the step size, or distance we should move from the position x0 to the position x1 along the direction d0. Since we already have x0 and d0, we just need to find alpha 0, which equals -gn transpose dn divided by dn transpose q dn. For n equals 0, we can find alpha 0 by plugging in g0, which is -3, -1. We'll also plug in d0, which is 3, 1, as well as matrix Q, which we identified previously as 5, 2, 2, 1. After performing this matrix multiplication, alpha 0 equals 0.1724. Next, we'll plug alpha 0 into our equation for x1, and our value for x1 equals 0.517, 0.172. Next, we'll check the gradient g1. The point x1 is a local minimum if g1 equals 0, 0. Also, to avoid confusion, vector x1 describes the location of a point which has the coordinates x1 equals 0.517, x2 equals 0.172. Therefore, we'll plug the coordinates x1 and x2, which makes the gradient at this new location equal to -0.692 0.2068. Since this gradient is not 0, location x1 is not a minimizer of the function f of x. Therefore, we'll search for a point x2, which generates yet a smaller value of f of x. Already we have x1, but we don't yet have alpha 1 or d1, which represent the step size and direction vector, respectively. At this stage, we want our direction vector d1 to be a linear combination of the gradient g1 and the previous direction vector d0. After plugging in these two terms, all we have left to determine is beta. We'll choose a value for beta such that d1 is q conjugate to all previous direction vectors, d0 to dn. If we plug in n equals 0, as well as the terms g1, q, and d0, our calculated value for beta 1 equals 0.00468. After plugging this value into our equation for d1, the new direction vector equals 0.0832 negative 0.2021. Returning to our equation for x2, we previously solved for the location x1, and we just solved for the direction vector d1. Therefore, all we have left to solve for is alpha 1, the step size, which is computed just as before, negative g transpose d over d transpose qd. After plugging in the appropriate variables, alpha 1 equals 5.81. After we plug in 5.81 in for alpha 1, x2 equals 1, negative 1. Next, we'll calculate the gradient at this new point to check if x2 is a minimizer of the function f of x. And after plugging in the coordinates 1 and negative 1 for x1 and x2, the gradient g2 equals 0, 0. This means the location 1, negative 1 is a minimizer of the function f of x. Therefore, the minimum value of f of x is found by plugging in x1 and x2, and equals negative 1. When reviewing the possible solutions, the answer is A.